in terms of valves, opening and closing, what happens at point A? AV open, B, AV closed, C, semilunar open, D, semilunar closed. So closure of AV marks the end of filling and the beginning of. Right, so line BC is isovolumetric contraction. At C, semilunar is open, pressure is going up, and volume is going down.
Ejection.
So this is ejection phase. Ejection ends with closure of semilunar valves. From D to A, no change in volume, just a drop in pressure.
Relaxation.
Isovolumetric relaxation. BC, isovolumetric contraction. AB, filling. CD, ejection. How about everything from D to A to B? Diastole. B to C to D? Systole. Stroke volume. You've got what you need to calculate it. What's the value? 135 minus 65, 70 mils is your stroke volume. Can you figure out on here where the first heart sound is occurring? Because you know where the valves are opening and closing, and that's what the sounds are based on. So what point represents first heart sound?
B&D.
B and D.
Love? What creates that sound? Closure of AV. So B? Point B is the first heart sound. And the second heart sound? D? Closure of the semilunar. Right, so pretty much everything you can find on the original cardiac cycle graph you can find here. The only thing that's not shown here, electrical activity. But other than that, you've got your volumes, you've got your pressures. You can tell when the valves are opening and closing, and so you can also figure out heart sounds. All right, so on your handout, the next pressure volume loop. It's really two loops superimposed on each other. And we're trying to figure out what has changed. All right, and there's three possibilities: preload, afterload, contractility. So the way to read this, start here. You have 60 ESV, you fill, you end with 120 EDV. Contraction, ejection, relaxation. All right, so 60 to 120, AV closes, pressure rises, semilunar opens, blood is ejected, semilunar closes, and you're back to your ESV of 60. That's loop one. Loop two, start at 60. Fill to 140, open the semilunar, eject, but you're ending at the exact same ESV as you did before. So what is represented by the gray area? We increased the preload. We increased the EDV from 120 to 140. Because preload went up by 20 mils, stroke volume went up by 20 mils. So the gray area represents both the increase in stroke volume and the increase in preload. And who was it that said that any extra blood you put into the heart, it will eject right back out?
Frank Starling.
I know it sounds like one person, Frank Starling. It's two people, last name Frank, last name Starling. That's why it's usually Frank hyphen Starling. Right? But that's the Frank Starling law or principle of the heart. So we put in an extra 20, we got an extra 20 right back out, stroke volume went up. 60 to 120. Contraction. Open semilunar, eject. Back to an ESV of 60. Number 2, 60 to 120 again. Open the semilunar valve. Eject, but eject more blood, ending with less behind in the ventricle. So a smaller ESV. Let's say it went down from 60 to 40. And this is a big hint up here too. So what just increased? Right, so you have preload, afterload, contractility. So the gray area represents an increase in contractility and therefore an increase in stroke volume. Right, and norepi, sympathetic nervous system, is responsible for that increase in contractility. And you can see that we were able to generate more pressure, and that's why we were able to keep the valve open longer, if you want to think of it that way, or think of it as in the same amount of time we ejected more blood. Time isn't on this graph, so we can't see what's going on with time. But you can think of it either way. So clearly, when preload changes, what is not affected? EDV, ESV, or stroke volume?
ESV.
ESV is unaffected. Only EDV is changing and therefore stroke volume. With contractility, what is unaffected, not changing? EDV. We're not changing how much blood we put in. We're just able to get a little more out with a stronger contraction. And this time the stronger contraction is due to what?
Epi.
But what's the result of sympathetic and epi norepi binding to beta 1?
Increased
What's different, giving us a stronger contraction this time?
stroke.
More calcium. That's it. More calcium is available. And you know what happens from there. More troponin binds to calcium. More troponin changes shape. More tropomyosin moved out of its inhibitory position, allowing more cross bridges to form. In the end, more cross bridges, more force or tension. And then here, we're ejecting more blood. That can only be accomplished with a stronger contraction. What's responsible for the stronger contraction here? No change in calcium release.
Stretching of the fiber.
We're just getting the muscle fibers closer to optimal length. And the length tension curve shows you as you get closer and closer to optimal length, tension goes up higher and higher. More force as you get closer to optimal length. So we start at 60, fill to 120, eject, back to 60, that's loop 1. Loop 2, start at 60, fill to 120. Now we have to generate more pressure to open the valve. We eject, but we don't eject as much blood. So now we're left with a larger ESV. So the gray area represents
Afterload.
increased afterload.
What if you read the graph the opposite way around? You could also see it as the gray area being the first step. So it would
But
be
if you
decreased
read it
afterload.
like this, the reason it wouldn't make sense is because you're ending at a higher ESV, not a lower one.
Uh-huh.
Because here, I know what you're saying, it's the same thing. You have a higher peak on one than the other, but here we're ending with a lower ESV.
Okay.
And here the gray area shows us that we're ending with a larger ESV in comparison.
Mm-hmm.
Also, notice the difference here. We opened the semilunar at 2 different pressures.
Yeah.
Here we opened it at the same pressure. But the way these are illustrated, the gray area represents the change in the second loop. All right, any questions? What may be causing this increased afterload? Why would the valve open at a higher pressure?
Increased aortic pressure.
More back pressure, higher arterial pressure on the other side of that valve, so it's harder to open it. Alright, so for the quiz, put everything away or at least flip all those papers over.
It's gonna be all this.
Quite as much illustration to show it. Channel B. Make sure you keep your clickers on your lap, out on the table, please. We put in a request weeks ago for them to raise this. We're losing all that top portion and they haven't done it. Bugging me. The screens are already so low because the ceiling's so low.
Hey, Trevor.
All right. Done? Well, that's decent. Done? Preload is completely independent of ESV. When preload changes, it's because EDV is changing, but nothing happens to ESV. Preload and contractility are two different mechanisms that increase force of contraction. Right? One's intrinsic, one's extrinsic, but they're not connected to each other. So you could increase stroke volume by increasing contractility, but you can also increase stroke volume by increasing preload. So you can describe preload as an increase in force independent of contractility. Contractility is an increase in force independent of fiber length. And with preload, that's what's changing, fiber length, getting closer or further from optimal. Time to flip a coin. What is I'll start broad. What's an inotropic agent? A chemical or condition that affects contractility, right? That leads to a stronger or weaker contraction. What would you call a chemical that affects rate of contractions, heart rate? Chronotropic agent. So if inotropy refers to strength, then positive would be stronger and negative would be weaker. In your body, which chemicals are primarily responsible for increasing contractility? So those are your endogenous positive inotropic agents, epi, norepi. What receptors do they bind to? Right, so that's how they increase contractility. They bind to beta 1. So if you have a beta 1 agonist, you're going to get the exact same effect, right? But if you have an antagonist or a blocker, you're going to prevent that increase in contractility. So beta 1 receptor antagonists are negative inotropic agents. Beta 1 receptor agonists would be positive inotropic agents. One more.
Why did I change my
So what's
answer?
the consequence of phosphorylating mice and ATPase?
No, I changed it.
Faster cross-bridge cycling, so a faster contraction.
Never changed
Right, you're squeezing on that blood at a higher velocity. Consequence of phosphorylating calcium pumps on the SR.
I knew it.
Faster relaxation. Why is it important at this time? And by that I mean when we have increased sympathetic activity, when epi, norepi are stimulating these receptors. Why is it important to have a faster contraction and faster relaxation?
Time.
We're losing time, right? Why are we losing time right now? Why is each cardiac cycle shorter? Because when you increase sympathetic output to the heart, you can't just increase contractility. What's happening at the same time? Heart rate's going up. And increasing contractility actually helps compensate for the reduction in diastolic and systolic time as heart rate goes up. You don't have as much time to eject blood, all right? So we need a faster contraction and a stronger contraction. So we're going to have to eject more blood in less time. You don't have as much diastole, you don't have as much filling time. Okay, then we need to do what we can to start filling a little sooner and get through that isovolumetric relaxation phase a little quicker. So the faster you relax, the faster you drop the pressure, and the sooner you open those AV valves. Calcium channels on the SR. To release more calcium for a stronger contraction. L-type calcium channels. Same purpose, but you have two sources of calcium, right? And we're increasing the amount of calcium coming from both. Bring in more from the ECF through the L-type channels, more from the SR from the calcium release channels. And sodium-potassium pumps are ineffective.
Constant.
If you think you may have lost a recorder, I have one on my desk, picked up the other day. Done? How about BC?